Guido fera son séminaire en anglais, mais il comprend très bien le français. Donc je vais le présenter en quelques mots en français. C'est un très grand plaisir de l'avoir avec nous aujourd'hui, à 2 reprises, à la fois ce matin et cet après-midi. Donc Guido est professeur à l'Université de Strasbourg depuis 2012 et il dirige là-bas le groupe de physique quantique à l'ISIS. Alors ISIS, tout le monde connaît l'acronyme, mais ce que ça signifie derrière, c'est Institut de sciences et d'ingénierie supramoléculaire. Voilà. Donc quelques mots sur sa carrière. Il a une carrière très très internationale. Master en Italie, à Bologne, une thèse à l'Université du Maryland, au NIST en fait, sous la direction de Carl Williams. Ensuite, à Innsbruck comme postdoc, puis senior scientist, et son habilitation dans le groupe de Peter Zoller. Et puis donc, depuis 2012, recruté à Strasbourg. Alors Guido a absorbé et abordé de nombreux sujets dans sa carrière. Je ne vais vraiment pas faire une liste complète, mais j'en suis mis quelques-uns sur mon papier. Il y a un sujet qui est en lien direct avec le sujet du cours de cette année, qui sont les gaz dipolaires. Tu avais écrit, Guido, il y a quelques années, même plus de 10 ans maintenant, un article de revue sur les gaz dipolaires qui m'a été personnellement très utile pour la préparation de ce cours, je peux le dire. Il s'est intéressé à la physique à N-corps en interaction forte, notamment les gaz indés, quelque chose que je connais beaucoup moins bien, qui sont les semi-conducteurs organiques, couplés à des placements de surface, donc couplés au champ du vide via les placements de surface. Ça, c'est un travail que tu as fait en collaboration avec Thomas Sebesen. Quelque chose dont tu nous parleras cet après-midi, qui est la conception de portes logiques quantiques, robustes, qui sont utilisées maintenant abondamment dans les groupes qui font de l'information quantique. Et puis, donc, ce dont tu vas nous parler aujourd'hui, qui est le couplage entre matière et rayonnement stocké dans une cavité. Et c'est donc le sujet de ton cours. Donc, je termine en disant qu'il a reçu de nombreux prix. Il y a eu une bourse versée en 2012. Je ne vais pas les citer tous. Hein. Mais disons, le prix Guy Horisson en 2013. Et en 2019, tu as été élu membre senior de l'Institut universitaire de France. Voilà. Donc, Guido, bienvenue et merci pour ton séminaire.
Merci beaucoup vraiment pour l'invitation. C'est vraiment un honneur d'être ici aujourd'hui et vraiment un plaisir aussi. So I see a lot of, is it maybe too high? Is it good? So actually I see a lot of faces that I know, and I'm very grateful that you're here. And so thank you very much for being here. It's really, again, an honor to be here in this lectures in this distinguished place. So I have to say that I may have now, realizing the kind of audience that is here today, I may realize that I may have, got it wrong a bit how to organize this thing, because I inserted, in fact, a lot of introductory material that connects different things. And so I think that instead I see not only a lot of people with certainly PhD in physics, but a lot of leading experts in the world about the stuff I'm talking about. So please just intervene if you think that it is just ground zero, and I will move on to many things. Okay, so again, it's a real pleasure to discuss here today work we did in the last 10 years about semilocalization of disordered spins in cavity QED. So this is our group in Strasbourg. We are blessed with many talented younger people, and also some permanent collaborators, and I want to just acknowledge their work. In fact, the work is done in collaboration with 3 colleagues from CNRS, Johannes Schachenmeier, David Hagemüller, and Jérôme Dubail. And Francesco Mattiotti was a postdoc. We are all sitting now in this new center, Centre Européen des Sciences Quantiques, in collaboration with KIT in Germany, which has been built recently, and Professor Dalibard delivered the keynote speech to inaugurate that, which was a wonderful event. So now actually it has already doubled, to double the size. So there are 4 new labs, brand new for quantum optics. There is nice office spaces. There is a very nice tree, which is not made in PowerPoint, but is actually true. It's nice, it's like that. So it's a very nice place to work. We are hiring, so if you know some young people who want to move in the east of France, you can consider it like outside of Paris, but without the area. So it's you can have a nice traject in 1.5 hours. You can get here 145 minutes. So it's actually a very nice place to work. And then we'd like to tell about the story that we developed there in this period. So the general idea is something that has been really driving this field for the last 20 years, which is useful quantum simulations. Now, there has been kind of a divergence of two different kinds of quantum simulations. One is about analog quantum simulation for scientific discovery. This is really mature technology that started maybe 25 years ago. This is basically only a study here is limited by our knowledge. The focus is you can ask many physics questions, exotic many-body phases, transport, light matter interaction, topology, high energy physics, boson fermions, etc. We just heard supersolides, which is really a demonstration of what you can do with this kind of system. This is really scientific discovery using cold atoms. Now, the other thing came up in the last also 25 years, but really just in the last couple of years, which is about digital quantum simulations for computing applications. Here you could ask, in principle, any questions if you were able to program a quantum computer. But in fact, we are just at the infancy stage. So this is limited by technology and knowledge. So the focus today is on technology development of quantum gates, control architecture, et cetera, and also applications. And so this is very burgeoning field. And all of this in our from our point of view, is from cold atom as a quantum simulation platform, both for analog and digital quantum simulations. I will obviously talk today about this part of work, but just to advertise this afternoon session, this is just a plot of two key elements for looking what is interesting to look at for quantum computing today. If you just look at number of qubit as a function progression as a function of here, you see that neutral atoms is shooting up very fast. Of course, we have these wonderful oscillators, which are the best clocks in nature, so that is a very good starting point to make a quantum computer. But if you now, the problem until recently for the neutral atom platform was, in fact, the fidelity of the quantum gates and then the control of all these beautiful identical quantum systems. But now recently, you see that the slope here is going very fast down and is reaching actually the other technologies, which are superconducting circuits and also trapped ions. So it's actually quite an exciting time for doing quantum computing. If you put now the key numbers for superconducting loops, trapped ions, silicon quantum dots, atomic qubits, you see that now the number of addressable qubit is about 100 in the best technology. But recently in atomic qubits, this has shoot up a few thousand, and up to 10,000 is not easy. We just discussed with Thierry before, not easy, but is also definitely not impossible. It's going to come. Up to 10,000 atoms, controllable qubits, this is happening in the next couple of years, for sure. And then also the fidelities of the gates now are on par with the other fidelities, but with possibility of doing multiple gates at the same time. So this is a very exciting time. There also has been demonstration of 48 logical qubits from the Harvard group. So it's really a great time to work on all this stuff. So read the workshop this afternoon. We are very happy. We've been working on this kind of field now. It's great to see it kind of exploding in a positive way. In fact, in Strasbourg, we are also building the French public infrastructure for quantum computing together, especially with Professor Shannon Whitlock, who is leading the experimental building of the thing, which is a definitely non-trivial thing. So the idea is to build a dual species architecture with potassium and also ytterbium atoms mixed in this kind of array. So you can do various things like data storage in one and reading out on the other one. On the theory side, we're looking at highly optimized universal gate sets and how to make it robust and how to implement it. But there are many, many physics questions which are very fun actually to look at. It's not just, definitely is not engineering problem only. This is really physics problem at many, many levels. And it's actually quite interesting way of doing that. We're also doing that for the European quantum flagship thing. So again, if you're interested in doing these kind of things, please, we're hiring, just little advertisement. OK, so that's it. This talk is about the other kind of things that we like to do, which is indeed many-body physics and understanding just nature and see what we can do with that using cold atom physics mainly. But in fact, there is a large community outside there who don't care about cold atoms, as you may have encountered people that don't care about cold atoms. So they maybe care to modifying material properties like high-temperature superconductors, a critical temperature high-temperature superconductor, by, for example, illuminating this by ultrafast laser pulses. This was a beautiful experiment by Cavalieri group, and there are many other people who are also here in Paris that are very interested in this kind of physics. This is a beautiful physics with also implication possible in technology. Now, in many of the situations, of course, nature is complicated, and so even the writing down the Hamiltonian of a high-temperature superconductor is a non-trivial business. And so, in fact, here there are fantastic experiments, and also, but maybe it doesn't have the natural flexibility of cold atom systems where you can actually engineer often the Hamiltonian from scratch. So our hope is to, and with us many other colleagues, we are very interested in getting kind of inspired by this kind of physics, and maybe reproduce some parts of it, some elements, something that we think is relevant into cold atom experiments, and in particular, where you can actually trap the atoms. We have heard from Professor Dalibard how well you can actually tune the interaction between them, change the kind of interactions, but also you can add the light field, maybe in a cavity, maybe using external powerful fields, or just even evanescent waves, or just the vacuum field. And so this can actually be used for many different situations. Our interest is to, in this talk especially, but also really in our group, is to look at problems of transport in disordered materials, and we see for what motivations. This could be interesting also for maybe if we get something new here, maybe we can go back and suggest new experiments also in the real world. So our starting point, indeed, as Professor Dalibard mentioned, is a collaboration that we started almost 10 years ago with Professor Thomas Ebbesen in Strasbourg and Paolo Samori. We used to, before we moved to the new building, share the coffee machine, and that was extremely important for starting collaborations. And exactly the coffee machines, about 10 years ago, I started this conversation about some interesting results that they had in the lab. And this was in their common lab for this experiment. So they had this kind of, from our point of view, our non-chemists, kind of complicated organic diemolecules that they kind of sputtered in a amorphous surface on top of a plasmonic structure. Now, the plasmonic structure, from say, a very far away point of view, is essentially a metallic structure that is perforated in such a way, in a periodic way, in such a way that you can structure the surface modes of this two-dimensional object. By changing the periodicity of these holes, literally, you drill the holes. When you drill the holes, you essentially select what kind of wave vector the surface mode can have, which are bosonic mode. Just these plasma modes are bosonic, and basically you change their wave vector, the wavelength associated with their propagation. And what this experiment has shown, it was a very interesting result, that they could inject current and have a current enhancement from the left to the right. You have here plots of current versus voltage, and you see that you have some baseline. The baseline is if you perforate this metallic structure with a random array, so you just place the holes randomly, and then this is basically what you get as a current on the other side. But if you do nothing else than perforating the thing in a regular structure, and you start changing the periodicity of the holes, you see that the current goes up. And then later experiments made this symmetric, so seems good. Also, they did similar experiments also for energy conductivity in these organic semiconductors, and this was kind of a bit of a mystery how it worked. We got interested, and we started discussing, and we collaborated in several works about these kind of things. The only hint for theorists was that only this happened, this kind of enhancement, if the internal molecular transition had the same wavelength of the allowed surface modes of the plasmonic modes of the 2D material. Only when these two lengths matched, then there was kind of a hybridization of the modes, and therefore also, and associated to that, seems to be an enhancement of current transport. Beautiful experiments, very complicated from our point of view. So we had the almost used to cold atom system where you could write down all the Hamiltonian from scratch. This was kind of another world of interest, because this is really exploration of new phenomena. But the question is, how do we understand this from a quantum many-body physics perspective? So there are many fundamental open questions, many degrees of freedom and possible effect. For example, the plasmons are no local. The vibration of the molecules are local. The electrons are both local and non-local degrees of freedom. From our point of view, as theorists, we needed some simple modeling, probably some ab initio simulations, which we cannot do. And also, we are used to, if you do a prediction, it's very hard. It's not like you can change any Hamiltonian parameter in this kind of experiments. And so therefore, even if you have a prediction, it may not be possible to test it directly as you would like. So our approach, after some initial collaboration, has been to, OK, let's stop and let's pick up one problem at a time. Let's take a simpler problem. The simpler problem is energy excitation. And we focus on the role of disorder in these systems. Why disorder? Because these molecular materials are actually extremely disordered in many different ways. For example, they don't form these molecules nice crystals, form a crystal with 20 sites, and then they break, and there is another little structure, and etc. So it's very disordered. in a spatial sense. But also they have molecular disorder in the orientation of the dipoles. So they couple differently within each other, with the field, the external fields, and etc. They have vibration. Each one of them has a natural dephasing, which is given by the vibration of the molecules themselves. So you have to add that. It's an open system by nature. So it's quite complicated to give a structure. So we focus, say, on the role of disorder, and we write down simple models from quantum optics. But then we can maybe test these ideas in a cold atom setup, and so suggest experiments that can be done and can test at least one of these elements. And that's what I would like to report today, because that's exactly what finally we were able to do after 10 years working on this. There is a written experiment by the group of Jean-Philippe Brantou, and also a parallel experiment by Jakob Reichel and Long here, and we are very happy that these collaborations went, and I would like to report on this at the end of this talk. Now, so this is where it comes that I may have actually got wrong at the audience here today. Because I thought, OK, this is a bit complicated and a bit technical. And so I think we need an introduction of what we want to do. At least for us would have been helpful. So before starting with really what we did, we would like to introduce the global type of things that we have around. And so more than half the talk will be introduction. And what we'd like to introduce is disorder-induced quantum phase transition and some specific thing that happens at the quantum critical point, which is multifractality. And these multifractal states will be actually what we claim is that actually are quite important every time one take cold atoms or any other quantum objects which is disorder and puts it in a cavity field. We claim that actually these kind of states don't only live at quantum critical points, are actually the generic state that you get if you put atoms, for example, in a cavity, and you have had some kind of disorder. All the states will become automatically multifractal, and we try to explain why. And these multifractal states have very interesting properties. And so then you have a playable, tunable system where you can play with these kind of exotic things that so far were mainly a theorist playground. Okay? So we would like to basically explain where this is coming from. You probably, all of you know, so please just tell me stop, okay, and move on. But I will start anyway. And then if you don't stop me, I go through it. And then at the end, explain what we did and give 2 slides of the experimental experiment at the end. If time remains, it will not remain. But if somebody is interested, I would be happy to add a twist to the last few slides of Professor Dalibard class, which was great, and add some other ideas of things that could happen in this dipolar system, which we've been close to our heart in the previous kind of few years. And we still have some ideas hanging around which could be interesting. So if you are interested, I'd be happy to give maybe a couple of slides on that, but during question time, because I don't think there's big time. So interval quantum phase cold atoms will be more than half of the talk. So, and now you see why I'm saying that this is basic, okay? The first slide, I didn't know where to start. So let's start from scratch. So we know that except, there are exceptions, but in general, there are 2 kinds of objects in nature according to quantum statistics, fermions and bosons. Fermion antisymmetric wave functions linked to Pauli exclusion principle. You cannot put two on the same state. These are electrons, quarks, muons, lithium-6, helium-3. Fine. Bosons, symmetric wave function. If you exchange the wave function, you get symmetric plus. These are photons, phonon, Higgs, mode, lithium-7, helium-4, and they Bose condense at 0 temperature. I'm going so fast because I know that you know it better than me, so I go on. Next, when do quantum effects come about? OK, very rough thing. The Broglie wavelength, it goes like the inverse of the mass and temperature, square root. When this is larger than mean interparticle distance, that's roughly where you expect things to happen. Cold gases, yes, here there's a world place for cold gases. So again, I will not insist on this point. The typical distances is about 100 nanometers. The mass is about that. You get temperature below microkelvins is where things get cold enough that becomes very interesting. And of course, Professor Dalibard and colleagues have been really at the heart of the development of the techniques that allowed everybody else to develop themselves and everybody else to develop this field by, for example, similar to laser cooling, where you shine light properly done to an atom, you can actually cool it down to microkelvin temperature, so you can go much lower temperature with other techniques. nanokelvin is very simple today in many systems. So then you can combine statistics and the bosonic thermal statistics, and now interactions. And of course, if you combine statistics and interaction, then interesting things happen. And this slide was just introduced for, if you never had heard before, but you definitely have heard before, the concept of quantum phase transition versus thermal phase transition. So for example, if you take the dipoles that we hear today, and you put them in a two-dimensional situation as we hear today, then you can have purely two-dimensional. So they're really fixed like this, perpendicular to the plane. Then you can only have this kind of typical phase diagram where if you go along this line, you start from some low energy state, and thermal fluctuations start competing with dipolar interactions. Now we have this d squared over a cube, d squared the dipole strength, dipole interaction, and then a cube is the interparticle distance cube. That's a dipole interaction. If thermal kinetic energy becomes comparable to interaction, you typically have a normal phase. And this is a classical thermal phase transition. But as we heard today, you can also have quantum phase transitions driven by the competition of quantum kinetic energy, which is h bar squared over ma squared, and interactions. So the order of the transition can be first order, second order, or we don't know, because in this phase diagram that we computed some time ago, we said it's probably first order. But in fact, theory says no. There should be actually an infinite set of states exactly here at the transition point. Nobody's ever seen them. It's within error bars, but it doesn't matter. So the point here is that there is a quantum kinetic energy that, of course, can drive a transition from, for example, a superfluid to a crystalline phase in these systems. As theoreticians, how do we see? How do we measure these kind of things? How do we compute? How do we measure? We have heard some beautiful analytical techniques that we hear today. There are also numerical techniques like quantum Monte Carlo that for bosons are exact, essentially. And so one can actually compute the many particle properties in an exact sense statistically. So for example, if now you have bosons, here's where statistics comes in. Of course, for weak interaction, you have a superfluid. And this is non-viscous fluid, as we heard now, due to both the statistics. These are BCs, helium-4, superconductor, etc. And if you have dipolar interaction, on the other side very strong, then you can crystallize. Now, these one are actually snapshots of many particle wave functions taken from Monte Carlo. So these are literally, the projection of path integrals on a two-dimensional plane. And the red thing is the mobility, is a remnant of the mobility of the particle there. So in this kind of computation, if you take a crystal, the center of this here is where, in average, the particle is. But in fact, what is more telling is all the red thing around, which is really a picture of the quantum phonons oscillating around, given by Monte Carlo naturally. When you see a mass, that's a mass here, like here. That mass is the superfluid. It's a picture of a superfluid, which changes all the time. Is a liquid, non-viscous. So these are really, how you would see it. You can measure things, but you can just see them also in snapshot of the Monte Carlo calculations. And we've seen today Professor Dalibard lecture series that, in fact, there are different kind of transitions. This has been shown now in weakly interacting gases as a competition of dipolar interactions, also with short-range interaction, confinement, and then we have given rise to this transition from superfluid to supersolid and even droplets, independent droplets. So I think this lecture was fantastic because this is, in fact, one situation of these supersolids here where really cold atoms has, for the first time, demonstrated something that was not known it was possible. So this is really a step. Now, again, strong interaction, ask me about it if you're interested, and we can talk about the end, but I don't think so. Now, there are other kind of phase transition which are not first order, as I said before, and these are, we are particularly interested today to introduce, again, because you probably know better than me, another class of transition, which are localization transitions. So in his groundbreaking paper of the 50s, Phil Anderson has demonstrated that if you take a three-dimensional system where you have quantum particles, say electrons, and you put them in an array, so in a nice crystal without imperfection, of course, the wave functions are extended. The system is a conductor, no problem. But if you have enough disorder is key to all these systems. It's in nature, in all these kind of crystals, there is always disorder, but also especially also in these molecular materials we were talking before. Then, in 3 dimensions, you can have a quantum phase transition that goes from an extended wave function to wave functions that are all exponentially localized. Now, this is, of course, this was at the time, people knew that disorder was not good for transport, but they didn't know that there was really quantum phase transition. Fine. So the typical Hamiltonian is this one. One can have here electrons, but can also have spins, excitations. We will mainly look at spin excitation. They also do the same. So these are Hamiltonian for a spin, hoping, for example, to nearest neighbor by dipolar coupling with a particle hoping energy J. And also we have a local disorder which measure the distribution here of disorder locally distributed from some distribution within a box. And this is the local energy shift that are given here. And so there is, in fact, a quantum phase transition between, if J dominates over W, there is particles are delocalized, we have a conductor. J is much smaller than W, we have localization and insulator. And we have a quantum critical point in between. And the quantum critical point is actually the interesting part here. But we will be interested in what happens at the critical point. So as, again, in theory, how do we analyze this kind of system? There are analytic techniques, numerical techniques, all of these are available. One key observable that is very useful here is the so-called inverse participation ratio, which is a measure of how localized a given eigenstate of the Hamiltonian of H is. This is defined basically as the projection. You take the eigenstate, you project it onto the basis of the individual side, see 1, 2, 3, up to n. You have a sum from 1 to n. You take the fourth power of this, so you take this momentum here, and then you look, you project on the spatial basis, and then you look. If the system is the wave function is delocalized, then this will scale like 1 over n. If it's localized, it will stay basically at 1, because it means that the whole wave function is sitting, at the single site. There is also other ways to characterize the various phases. For example, the level statistics, we will see it below. But this one is a very useful one for what I want to say next. Next, I would like to say that some of these things have been observed early on in cold atoms. There was beautiful experiments here in Palaiseau by the group of Naspe. They trapped a BEC in a one-dimensional waveguide. They added some speckle potential to do some disorder. And their observation is that, indeed, disorder will localize exponentially the wave function. And here we have a picture of the fact that they have their BC that could expand here, but because of disorder, it stays put, and for a couple of seconds, it stays exactly where it was. Now, there was a parallel experiment in Florence by a group of Inguscio, Modugno, and all other people who also, like here, they're all now professors now. So all these people here, you find them in different labs now because they all found good careers. So this was one of the reasons why they got a good career, was this kind of experiments. And there, they had a different situation. They, instead of imposing a speckle potential, they had first an optical lattice, a regular optical lattice. And they added a second optical lattice, which was incommensurate with the first one. And if you sum the two lattice potentials, you obtain a quasi-random potential. If you choose it properly, if you, in general, if you find a system, you can take whatever, what you want. You don't find resonances, really. If you have a large system, you have to be careful what you put. But then, and then essentially in this bichromatic potential, you start seeing that you have local energy shift given by, the fact that the two lattices are incommensurate. You get a local energy shift for this reason. So now these are experimental data. They start at t equal to 0 time. Disorder strength increases in this way. And then we can see the following. They start at t equal to 0 with a BC. And then they let it expand in the 1D dimension in the presence of these lattice potentials. And you see that in the case of J being much larger than W, the atoms could expand. In the case in which W was much larger than J, they have to stay put. They were localized. And this was a signal that something was happening in between. Actually, this model here, if properly tuned, has a quantum phase transition, also in one dimension, which is the Aubry-André-Harper model, and has a quantum critical point when these two scales compete. So this is really coming from the competition of kinetic energy and disorder. The question is, good, how do wave functions look like in not only here or here, but also at the critical point in between these two states? Now, the wave functions at through the conductor-insulator transition typically look like this. They could be one dimension or three dimension, doesn't matter. You can plot it the same way. This could be the Hilbert space, for example, for one particle. If you take a single particle wave functions, then the Hilbert space or real space are equivalent. OK, so if you have now in the weak disorder, let's take 3D Anderson model or the Aubry model that the AEH model here that we saw now. If you plot the wave function in the delocalized phase, it will kind of fill, the whole space which can fill. It's like, it will go everywhere. It will be totally ergodic, and it will fill the whole space. If we have strong disorder, you will see that the square of the wave function will be concentrated at some point, where some heat spot here. The point is what happens at the critical point. Precisely at the critical point, which is hard to probe experimentally, the states will become very interesting. These are turns out that people have studied this in depth, and these are multifractal states of the critical wave function. Critical means at the critical point, so have particular characteristic there. But the states themselves are quite special because they are intermediate between a completely delocalized and a completely localized states. They share both of them, so they are delocalized, but not necessarily ergodic, and they have other properties that are quite interesting, we will see below. So these multifractal states are pretty exotic states, which are intermediate between localized and non-localized. They are predicted to exist at localization transition, not just Anderson localization transition due to disorder. It could also be integer quantum Hall effects, some kind of theoretician power law-binded random matrices, and other objects that people have developed in order to study these kind of systems. But usually this has been confined to the theorists. Okay, so there are not many experiments who are able to exactly probe the critical point. In particular, in cold atom experiments, these kind of states have not been tested. There was a beautiful paper recently, actually, from Jacqueline Bloch, Alberto Amo, Zillberger in Nature of Physics with AAH transition study in polariton, but the focus was slightly different, but actually we used one of their pictures. And one of the pictures is this one, because if you want to understand why they are special, these states, you can just look at this picture here. These are a computation between 100 sites, and then you look at the square of the wave function, so it's bound to 1. And in the presence of disorder, because of disorder, this one is essentially peaked here at 1, as 0. But then you see that there are other peaks all over the place. And if you could zoom in from here to here, you will see that in the neighborhood of this, will look like there are more of these states close. There's other peaks that you find here. And if you zoom again, you will find more of them. And this is the more you go in a larger system. So at the critical point, so this is interesting because this is a very unusual type of self-similarity of the critical states and the Neanderthal transition, which is kind of a very interesting feature of this kind of states. This is enabled at critical point by the fact that critical fluctuation extend over the entire system precisely at the critical point. So fluctuation can talk to each other at arbitrarily large distances. Now, this is recorded or not? It is. Oops. OK. I'm going to say it anyway, and then people will, because when you give too much interpretation, then it's better shut up and compute. But let me begin with small interpretation. So you have now your disorder system, and then you have this fluctuation and transition point, and they start talking to any length. So basically, if you have fluctuation here, it can pick up fluctuations at any other distance, and therefore, how to say, hybridize states which are at arbitrarily large distances. And that's actually the reason why. Please don't record this piece. This is the reason why you get this multifractal structure here precisely at the critical point and not in other places usually. The way in which you characterize now this kind of states is through, again, this now a generalized version of this inverse participation ratio. So this is exactly the same thing we saw 2 slides ago. But now instead of just taking Q equal to 2, you let it vary. And then turns out that fully delocalized states still decay like 1 over n, like in a metal. Fully localized states still have a few components of order 1, like this one. But multifractal states decay like a power law, but with multifractal exponent that depends on Q. And if this tau Q is not 0 and is not Q minus 1, then, we will see below, this is the definition of multifractal state, which implies the presence of this kind of self-similarity, and also determines, these are quite interesting because they determine what kind of states you have. And we will see below that we have a specific way in cavities. So we will come back to this one and compute it for the cavity system we talk later about. And we explain why, in that case, this is a very good measure and it'll help us classify what we are seeing. this I should really skip before I hang myself. This was made like, okay, if you want to understand why, let me say it, just one second. If you want to have a classical analog of this thing, of course it exists. It has been, fractal states have been developed for mathematics for many different reasons. And so let's just go there. This was, Mandelbrot, of course, had popularized this and also, of course, gave very important contributions in the discovery of fractal states and also multifractality. And the point here was the following, that if you want to approximate a simple geometry like this one, a round thing, a circle, with some rods of smaller and smaller length L, then you can do it very easily. It's a regular shape. Yeah, this will converge very easily. You decrease the coarse grain size from a large triangle to this small, 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 small. Then it converges to the true length of the circle. But if you take a more complicated structure, like, for example, the coast of Britain, that was a very nice example that he had, and you want to estimate what is the length of this coast, the more you decrease the size at which you look. From far away, easy, I can compute it, and it will look something. But if I start at a closer distance, at the centimeter scale, I will look, a leaf and everything else. So I will look more and more details in such a way that actually, it doesn't converge. If you make smaller and smaller scales, it does not converge. It keeps diverging. And the way in which it does it is exactly, given by power law with a dimension which is larger than 1. And this is very similar because this kind of is part, the self-similarity is built here. If you start looking here at details of this, of the coast, and we go at smaller scales, you see more details that look the same. And this is part of the self-similarity that we also see in these quantum wave functions, in a sense. We see something actually in multifractality because these wave functions are a bit more complicated. They don't have just one simple scale. So multifractality helps you to give us a continuous spectrum of exponents that helps us to understand more complicated structures. For us, the complicated structure we want to understand are the moment of the square of the wave function. Basta, the time is finished, so I think we can go. We can almost go. So we have 20 minutes to do really what we did. But so what we did was indeed inspired by the collaboration with Thomas and Paolo Samori. But again, we didn't now focus anymore on charge, which we looked at in some other works, but on energy. So study of energy transfer based on cavity QED. Now, again, I'm preaching to the Pope, so I'm not going to insist too much of what I see Professor Michel Brun and other very prominent people who have been developing this in the years. So, but then we have to introduce a strong coupling regime of cavity QED. So effectively, if you take two mirrors and these mirrors are good, you can have photon bounce back and forth many times and interact with a quantum emitter. This can be an atom, here represented by two-level system. Ground state, excited state is basically a spin, and then excitation, and then you can have coherent excitation from the ground state to the excited state by absorption of the photon and re-emission into the field and etc. So you have coherent excitation, coherent transfer of excitation between the photon field and the atom, described by James-Cummings model in certain regimes. This is the simplest model to describe these light matter interactions here. So the typical Hamiltonian has a spin Hamiltonian, and then a photon Hamiltonian and photon energy, and then the coherent coupling of light and matter. Clearly, if we are in the strong coupling regime, if omega, which is the vacuum Rabi frequency, which depends on the dipole coupling, among other things, is much larger than the bad stuff, so spontaneous emission and also loss from the cavity, then we are in the strong coupling regime. This is great because then you can do very interesting things like quantum optics, quantum information. And one thing that you will see in experiments, if you do a transmission spectrum, so if you transmit some probe light from here, you will see the formation of polariton modes with a splitting that is proportional to twice the Rabi frequency. Now, you can do a lot of quantum linear optics and quantum information in these systems, and it's very exciting. So exciting that our colleagues here got a Nobel Prize for it. So now, these polariton modes are coherent superposition of light and matter. Okay, that's a key point. Now, in the experiment, in solid state, typically you are in a situation where you don't have these very strong light matter couplings directly, and especially you have a gazillion, a microscopic number of actually carriers. So that can be excited, for example, from a valence band to a conduction band of a semiconductor. You can excite many electrons here, which leave a hole behind. You have a basically spin system again. And now you can couple that to the cavity, but you have a macroscopic number of carriers, and you have collective coupling often. So this is captured by modification of the previous Hamiltonian, which is the Temis-Cummins model. For multiple spins, the Hamiltonian is here. You have now energy for each individual spin, photon cavity, and then the coherent coupling between the cavity and the collective spins now. Now, the key point is the collective aspect, g square root of n. So when this is much larger than gamma and kappa, you have the formation of polariton modes. Great, and you can do a lot of stuff with that. At the same time, if you want to do quantum optics, quantum information, you don't know, because you are typical in the linear behavior, and there is if you talk to the cavity of the material, the people interested in changing material properties using collective coupling, they will say, oh, but why anything could ever happen if you have effects that depend on 1 over n? I mean, you're given a coupling, yeah, you have collective coupling, polariton splitting, but at the level of single particle, nothing really happened. So why are you even doing this, right? So that's a typical comment that people get when they do experiment. Experimentalists don't care, and they're right, because they do experiment, they find fantastic stuff, then they get a Nobel Prize. But theorists are in a problem, we have a problem, because the point here is always like, okay, you have 2 dark states, and 2 polariton states, but you also have n-1 dark states, which is a Godzilla number that do nothing. At the level of single particles, these are inert, so why do you care? Well, let's go back to disorder spin. I would like to give one example where, in fact, the formation of the polariton mode is associated to macroscopic changes of everything. So back to the basic Hamiltonian. Basic Hamiltonian, again, we want to study energy transfer disorder materials. So we have a hopping of particles from one side to the next, given by dipole-dipole interaction. As we said, disorder, diagonal disorder, off-diagonal disorder, spontaneous emission, and dephasing are all bad for transport. So if you take, for example, a 1D chain, and here we are entering theorist regime, 1D chain with disorder, and you want to transfer energy from a hot bath to a cold bath, you insert from the left, take out from the right, you plot the current here as a function of the distance. You see it goes down exponentially in the steady state, and of course it goes down exponentially because the eigenstates are localized by disorder. So you expect that that's a net effect in some macroscopic transport property due to the fact that the wave function, as we said now many times, are exponentially localized by disorder. Good. We are in 1 dimension. Again, we take the Anderson-Hamiltonian. In 1D, of course, all eigenstates are exponentially localized. Here are a few examples, square of wave function versus size. So localization leads to transform being suppressed exponentially as a function of length. Good. This is the other way in which we can characterize the various phases. For example, in a 3-dimensional Anderson model, if we are in a fully random case, so if W is much larger than J, it's well known that if one looks at the statistics of consecutive energy levels, and it plots it here, and look at the statistics of how this is distributed by Poissonian. This is a typical thing that if one could in experiment measure this, we say, oh, this is a localized system, boring. Well, boring, I don't know. Depends on what one wants to do. But this is what it is. Instead, if one is now in the conducting phase, the level distribution is well known to be of the Wigner-Dyson type. What is it? Is this function here. If you plot the statistics, so the probability of how close they are, the neighboring levels, if you put it here, you see that yes, so there is some decay here, but at short distance, unlike here, you have that this goes to 0. So there is some level repulsion. What does it mean? It means that if you have 2 spins, for example here, they are coupled by J, they hybridize, they repel each other, and therefore they are never very close to each other, because if they are close to each other, they talk to each other, and therefore you have some level repulsion. This is a typical thing that you find in a conductor. So what does a cavity do? If you now put the system the cavity field, and you have the photons, you have now this Hamiltonian that we have just seen. So this is a Tevis-Cummins Hamiltonian, now with this local disorder. Okay? So we have Tevis-Cummins Hamiltonian, very clear, with disorder. What is the effect of light-matter coupling here? Well, we have the formation of polariton modes, exactly as expected. So we have the formation of the light couples to the collective state, which is a bright mode. This is a collective coupling to the collective state with a 0 here in the phase. And you have the formation of 2 polariton modes, which are 2 states that get split up, one down. And this is the upper and lower polariton. If you now plot the wave functions for these modes, you have square of the wave function versus site. You have a typical dark state is exponentially localized. But the polariton mode is delocalized. Yeah, OK, fine. The photon field is delocalized. So why should be this surprising? It's not surprising. In fact, it's not surprising, but the result could be interesting because a few years ago, we've shown that in this situation, you can actually turn this exponential suppression of current into some power law, which can be still technologically useful, and it has its own interest. But the physics is very simple, so that for any collective strong coupling, you can turn a macroscopic thing from being a complete insulator to a conductor, which is not a fantastic conductor, but nevertheless. And this by exploiting the coupling to the polariton field. OK, so nice, but really interesting? Yeah, I don't know. It was interesting at the time, but then a posteriori you say, well, it's, you can just do perturbation theory basically with the polariton mode in and out. You expect to have that kind of scaling. OK. But then more recently, we started, actually, we had already in the original paper this idea, which is the following. Actually, yes, there are the polariton modes. And yes, there is a godzillion number of dark states. But because of disorder, in fact, these dark states cannot be dark anymore. They have to be gray. And that you can, by perturbation theory, you can very easily show that, in fact, disorder admixes a little bit of light into each of these dark states. Of course, just a tiny bit. But you have a godzillion number of these states which are now not dark anymore. They are gray. So the question is, how do the dark state, can the dark state now contribute to modifying transport in more complicated material? And the question is, what happens to undersolocalization in the presence of this delocalized photon field that now is talking to all the dark states, thanks to disorder? So now, in the next few minutes, I just go through the following thing. First of all, let's focus just on the dark states. They usually do nothing. But now just let's look at dark states, and let's look at stuff like a return probability. So if you put now a particle here at some given site, disorder, one way to decide whether the system is localized or not is just you wait for a long time, and you see whether the particle disappeared or not. You can do it also numerically and plot something that looks a lot like an IPR, but is slightly different, which is the time average return probability, which is, again, the projection of an eigenstate onto the basis set. But then you average over the states to the fourth power. Fine. So you plot this thing here, which basically is what happens at infinite time if you put an excitation here. Will it stay or will it not stay? And then you do it for a bunch of in 3 dimension in a cavity for the emitters. And this is plotted here. So if you expect to have 0 if in a fully delocalized phase and 1 in a fully localized phase. But what we find is that, in fact, for any strength for light-matter interaction, the system seems to form this kind of plateaus. And this plateaus is not a finite-size system. It's actually what happens. So there is something qualitatively changing at the level of the wave functions. And now, with all the discussion we had before, now we know what that is. This is the first instance of the particles being semi-localized. What does that mean? Again, if you don't have light-matter coupling, this Hamiltonian is just Anderson-Hamiltonian, strong disorder, wave function exponentially localized. But if you put light-matter coupling and you go in the strong coupling regime, which in this case is the competition with the disorder, then you have the formation of the polariton modes, yes. But all the other eigenstates also inherit a little bit of this light. And this light now acts to do what the fluctuations were doing before. It can couple any spin and any distance. We are engineering resonances at arbitrarily large distance in the system. So this has to be a semi-localized state. It has to be a multifractal state. And this is what is plotted here. This is, for example, this, if you take this triangle here, you see essentially is localized here, but also a little bit here. And if you have the round is here, 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 here. So this localization, yes, but on multiple sites is exactly the hallmark of semi-localization. And so this is the reply of what can happen if you just stay in collective strong coupling. Oh, nothing happened at the level of single particle. No, wait. In nature, we don't know. But in these models, for sure, everything changes. Because if you now put a light-matter coupling that is finite, and maybe in the strong coupling regime, but also weak coupling, but saying the strong coupling. Yes, you have if you take this, if the gray lines were your original width of disorder, you have all the states which were distributed in a Poissonian way before. But now, because of the formation of the polariton mode, you take out the polariton mode, and all the other states have, of course, to be orthogonal to that. And by being orthogonal, they are pushed inside in between the original states. Result? Well, the result is exactly that the eigenstate, if you look at the IPR, will not be 1, will not be 1 over n, is some other number. And this another number is exactly a direct measure of the semilocalization we are looking for. So if you start looking at things like what is the statistics of these states, doing the same game we did before, we now see that if you look at the statistics of consecutive sites, you see that now is neither a Poissonian nor a Wigner-Dyson, is a semi-Poissonian, hence the name. So it looks like a Wigner-Dyson along, or Poissonian along distance, but a short distance, you have level repulsion coming from the hybridization of the states by the photon field, and which actually hybridizing at arbitrarily large distances. So you always have a level repulsion as 0. And this is a well-known distribution that, in fact, was studied for the reasons of the Anderson-type localization by Bogomolny and other people. And we find exactly the same here in cavity QED disorder systems. This was not meant for that, but it works. So now, turns out that these systems are also turned, another macroscopic thing that we observe numerically, this one, is that they also turn diffusive. They were exponentially localized by disorder, but now even the dark states have enough photon field to become, in the thermodynamic limit, if you go to large distances, diffusive. But diffusive in a very weird way, because it's not like every single particle locally starts moving. It's just more the global probability raises up in time. So, but in time, you'll be finding a probability of finding a particle at arbitrarily large distances by a diffusion which is essentially linear in time. So it's a bit peculiar way of diffusing, but nevertheless, it's a diffusing system. This also now have a, I'm not sure. This was good that it was recorded, but fine, because there are many discussions about what that means exactly. I'm almost done. So I'm already past my time or not? Yes? No? Okay, sure. So now, instead, it comes where I'm very happy that you are all physicists, and actually eminent physicists now, because so I can actually allow to show the next couple of slides. Because now we can actually, because the system is actually quite simple, we can make it more simple and solve it exactly. That's what we did recently with Jerome, Thomas, Johannes, and David. So we take the same Hamiltonian. Now we eliminate direct hopping of the particles. We just take the Temis-Cummings Hamiltonian with disorder, and this can be solved exactly, which is what we do. And if you plot this one in form of matrix, it looks like a so-called arrowhead matrix, where you have only diagonal element, everything 0, and then here you have this arrowhead, which is the coupling to the light field of each side. This matrix is very well known in many different systems and is exactly solved. And we can use the fact that we know everything about this matrix, the eigenstates, the function, etc., to also solve the statistics problem using random matrix theory in large n limit. Turns out that this is an instance of a more generic central spin model, where now the central spin is the photon field. So imagine that now the problem is actually quite simple. We have a bunch of spins which don't talk to each other except through the central mode, which is, in our case, the photon field. This is basically the same as disorder spin system with a central spin, and you want to study, for example, an impurity in a bath of other particles. That's the same kind of problem, except that we have a bosonic mode in the center, but in the limit of just one excitation, that doesn't really matter. So this kind of Hamiltonian is actually a very large application in many different systems, also in solid state, but also in mathematics and control theory. So one can solve it, and if you solve it, you can actually show the following thing. Here we are plotting actually the inverse of the light-matter interaction strength, but say we can increase this number or decrease this number. And one thing that we can look at is, again, the level spacing, the statistics of the level spacings as we have seen before. Now, turns out that if you increase light-matter interaction strength, you can go continuously from a Poisson distribution typical of localized modes if you don't have light-matter coupling to a semi-Poissonian, which is typically of these critical states, which we are engineering without a critical point. And you can have any distribution in between, which I think is quite a nice situation where maybe the first time that actually I know of, where you can change the statistics actively, continuously from one to the next, and which is quite interesting. You can create your own critical states, which is living somewhere in between here. And now we have, again, this kind of thing that we have seen before. So how do we characterize the states? These are multifractal states. So again, we look at the generalization of the inverse participation ratio, which is looking at the higher moment of this sandwich. And now there are results that tells you that if this decays like 1 minus Q, then this is essentially like 1 over N, then this is a metal. And it is an insulator if a few components are of order 1. But in fact, this is defined as multifractal is if there is a qualitative change of the APR as a function of Q. So if you change Q, also this one change. And this is a signal of multifractality. And you expect that the multifractal state will decay as 1 over N as a power law, which is neither 0 or Q minus 1. Because it's exactly solvable, we can actually analytically compute this, and whatever that is, we find that polariton states indeed are multifractal. But more interesting are the gray states, which are multifractal in an interesting way. If you look at how these states are multifractal, you will see that there are two regimes. If you take Q, this power that you put larger than 1/2, this you will have a few of order 1, which is an instance of localization. So if you take exponents here that are larger than 1/2, this looks like a localized wave function. But if you take Q less than 1/2, this decays down as a power law, like a conducting state. So this in the absence of any phase transition. And the way in which it does it, we are just now focusing on the gray states, and we are just plotting this function tau Q for the gray state. Forget about what it is. It's just that basically the dark states are this gray line. It goes like here, and this is saturated to 0. Now, this function here, is actually related, tells you something about the nature of the states. You can classify the states, what kind of states these are, but practically what it's saying is the following thing, that if you now take something called anomalous dimension, whatever that is simply how much this exponent deviates from the one of a regular metal. It tells you this is a regular metal, this is how much, if delta Q is different from 0, then this is not a regular metal. Now, the way in which this is not a regular metal is identical to the Anderson transition in the infinite beta lattice, which is the closest thing to the mean field that we have for the Anderson transition. So the Anderson transition does not have an upper critical dimension, whatever, but the beta lattice is a mean field type, Anderson transition, and all the states that one can create in the cavity are all of this kind. And you can tune them in the lab. I think it's interesting. And as a result, actually, as a macroscopic thing, you can actually, if you didn't have too many losses, you could use disorder to enhance your transport when disorder is of the order of 2G. This one can show, again, analytically, this is a kind of a plot of the average current now from the left to right, done with Keldysh techniques. Here is disorder, here is hopping, and here is light matter interaction strength. You see in this heat map that, along this line, when the two scales compete, then you have the best current. And that's exactly, then you can engineer a situation where actually disorder can enhance the transport of the excitation in the cavity. Now with this, so in fact, one could go back to this paper here and actually show that you have the same scaling 1 over n squared also for the dark states, which is not something we knew before. Basta. In the next 2 hours, okay, but in the next 2 minutes, I would like to show what was done experimentally. This was actually done in collaboration with Jean-Philippe Brantou at TPFL and Philippe Auke as theorist in Trento, but actually there are also parallel experiments by Romain Long and Jakob Reichel, and we're very happy to acknowledge discussion with them. So, in Jean-Philippe experiments, the thing is a bit like the Florence experiment. So he has now 2 counterpropagated laser beams with slightly different wave vectors, length, typical characteristic length, they form a quasi-periodic structure. The way in which it does it is, they put lithium atoms, and then in more, they have a cavity. So now the red light is commensurate with the cavity length, and it is on this kind of transition here for lithium-6. The blue light is on the second transition here, and effectively what the blue light does, it gives a spatial dependent light shift to the excited states, basically making now, because the atoms are now trapped in each well, cannot move, then this provides essentially a disordered spin system exactly as we had before. And in fact, the effective Hamiltonian is the Davis-Cummings model. So you have a photon field with a center cavity atom detuning, collective strong light matter coupling, big S, which is the collective spin coupled to the photon field, and the local disorder given by the superposition of these two wavelengths. So like what was done in the group of Romain and Jacob, also in the experiment we contributed to, they looked at the photonic susceptibility. So basically what they had a weak probe beam that does cavity transmission spectra, and these are the spectra. So if you have, as a function of probe cavity detuning, so these are typical experiments for 70 and 150 atoms, and you see that experiments in theory without fitting parameters, so it's all exact. Then now what you can see in the experiment is that if you have zero disorder here, then you have the two polariton states. In both cases, they're shifting. They should, because g square root of n twice is the splitting. So you see the two polariton modes. But if you increase disorder strength, you start seeing this depopulation of the polariton modes and population of these intermediate states, which are the dark states that you have in between. Nice. So this was a demonstration of gray states that maybe in quantum optics people will say, well, okay, these are intersub-band states. Well, yeah, you expected to have it. Yeah, posteriori you expected to have it. But actually, if you change community and you go to these other communities that are interested in changing material properties, you tell them that actually you are able to populate the dark states, you will start discussions immediately. This is clear demonstration you can do that. Another thing you can do is you don't have to stay essentially resonance with, so you don't have to realize this Hamiltonian here. You can realize also an off-resonant Hamiltonian where you have the photon field of the cavity strongly detuned from the atom transition. Now what you are left with, you eliminate the photon field, you're left exactly with this type of Hamiltonian here, which is also very well known to theorists that love this kind of Hamiltonian. We love this kind of Hamiltonian. It is Lipkin-Meshkov-Glick model with a longitudinal random field, which is a subcase of a solvable Richardson-Godin model. So you can actually realize this experimentally. This is, again, you have some field here, and you have now a direct exchange of excitations from any spin to any other spin mediated by the cavity field. So the coupling is J, which goes like G squared, the light matter coupling, over the cavity detuning, so it's second order hopping of excitation from one side to the next. And here, in solid state, they would call it a ferromagnetic gap, whatever that means, gap here. It's not gap, but they call it like that. So basically, you have an effective ferromagnetic infinite range spin exchange interaction. And this kind of Hamiltonian has been used to model, for example, grain superconductors for many years and try to study those kind of systems. This is the last slide, and I would like to just show what Jean-Philippe group was able to do. So in theory, we were able to bound the linear optical response of the system by two lines. So here what we are plotting is essentially the atomic side of the response of the system. So if you shine light with a probe, and you will sometime excite the atoms. The atom will decay. They can decay to the ground state. They can also decay to another state. When they decay to the other state, you can actually detect that state, and so which will be the population of that state will be proportional to the total population of the excited state, and so you can trace back the excitation probability by measuring the population in a third state, which is kind of an ancilla state. Here, the two lines here were the theory without fitting parameters for two things. Our predicted theory linear optical response calculations by Green function, whatever, and the PR, which is the inverse of the inverse participation ratio. So it's a participation ratio. Now, that one is here, and that one is here. And it was possible to bound to always say that the experiment should always be above the participation ratio. But now we know that the participation ratio, from all the discussion we had before, if the system is completely delocalized, the zero disorder should be 1, and if it is at if it is a semi-localized system, should be fully localized system should be 0. Anything in between should be a semi-localized state. And in fact, experiments, the more increase the W over NJ ratio, you see that the linear optical response decreases, but stays bound within these two lines. And anything which goes bound, and especially along this line here, this is for 300 and 600 atoms. If you the fact that it goes along this line, this is actually is an indirect but almost direct measurements of the PR for the first excited state of an interacting many-body system, which I think is quite interesting. It's not a 100% proof that direct proof, but it's a quite convincing indirect proof of the formation of these semi-localized states in these systems. With that, I really have finished, and I thank you for your patience. The conclusions are that we have theoretically demonstrated the semi-localization for disorder spins in cavity QED, where you have now tunable multifractal states without a critical point. And you can actually play with that now to do stuff. You can play with it to maybe study many-body localization in very weird situations. You can think about designing electronic devices based on engineered multifractality and transport in disorder materials, which is something that for theorists is very interesting for people building devices. I'm not sure. We tried to talk to some people doing that, and we're not enthused. But also maybe one can give new prediction for cavity-modified material. For example, there is the effect of disorder in quantum Hall materials, like shown by Cristiano Ciuti, Jérôme Faes, and Scalari. It's a beautiful experiment. Maybe there is a space also to say something about the role of disorder in light of these results. With this, I would like to again thank all these collaborators and thank you all for going through this journey here. Okay, thank you.